All right, so this topic of periodic trends is why everything works the way it does in the periodic table. After you understand this concept, you'll be able to predict things by just kind of looking at the periodic table. You kind of be able to tell how things kind of work. It's a really interesting chapter. They're general trends, which means that we're going to go over some stuff and it's not always true, but generally it happens this way. All right. So atomic size is the first thing we're going to talk about, and atomic size is basically just the size of your atom, and it includes the electrons. All right. So the electrons spinning around take up space. The nucleus doesn't take up much space, right? Because it's really tiny, but that's where most of the mass is. But if we're talking about the size of an atom, most of it is where the electrons are moving around, okay? So atomic radius is generally stated as being the total distance from an atom's nucleus to the outermost orbital of electrons. And it's similar to kind of like if you had the same atom bonded to itself, the distance between the two nuclei, that's also kind of a way that they determine the radius of it in there. But I just like to think of it as just kind of like you have the center of your circle here, and then to the outside, there's your radius, okay? What the trend is, does it increase or decrease as we move across the periodic table? That's what we're gonna kind of look at for this trend. So let's compare some things. We're gonna compare three atoms in the same period, lithium, carbon, and neon. They're all neutral atoms, since we're going to assume that they have the same number of protons and electrons for right now. Okay, so they're going to be neutral. And then let's draw them, all right? Do me a favor, hang on with your, we can draw the first, I guess we can draw them together. Don't draw the second one yet. Lithium, how many protons does it have in its nucleus? It has 3, right? You look on there, you see it's the third one. Okay, so it has 3 protons in its nucleus. So I'm going to just write 3 plus, because that's going to be kind of the representation of the nucleus right there, that it has 3 protons. And we can say that its nuclear charge is +3, right? Because there's 3 protons. Does that make sense? Nuclear charge +3. Okay, how many electrons can you have in your first energy level? 2. How many electrons does lithium have in total? 3. So where's the third one go? Second energy level. For right now, we don't have to worry too much about drawing them in the correct locations, but this looks pretty good. First energy level has 2, second energy level has 1. We're okay with that, right? All right, let's move over to carbon. How many protons does carbon have? 6. Do me a favor, don't draw it yet though, okay? So it has 6 protons in the nucleus, and again, don't draw it yet, all right? How many in the first energy level? 2. And then how many in the second energy level? Don't draw it. All right, so we're okay with this, right? Why, if you look at the sizes, why would the first one be larger than the second one? I didn't do it on accident. I made sure that this was larger than this one, even though they have the same ratio of protons to electrons, right? Why do you think that that could be? All right, let's draw the well, you guys can draw this as long as you make it smaller. All right, let's draw the last one and we'll do the same thing. The last one was neon. What's the nuclear charge for neon? 10, good, yeah, there's 10 protons. And then we'll have 2 electrons, right? And then how many electrons in the second energy level? We got to get up to 10. We just have 2 there, so it's going to be 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. And if you notice that one, it should be even smaller than the middle one. So the trend here is that it gets smaller as you go across. But the question becomes why? What increases as you're moving across? The electrons, the protons. The distance decreases though, right? The distance is decreasing as you go across here. Look at the nuclear charge. As you go across, it's increasing, right? Which means there's a lot of positivity in one spot. In the center here, there's a lot of positive. And as you go across, it increases. The electrons are kind of on their own, right? They're spinning around. Sometimes they're doubled up, but they're all negatively charged, so they don't want to be near each other, right? And if you can kind of think about it, this +3 is pulling on these electrons, right? But that's only +3 pulling on 3, and you're like, well, it's even, right? But remember, all that positive is in the same location. Here there's 6, and then here there's 10. So each of these electrons is getting pulled in closer to the nucleus because of this nuclear charge pulling in at one point, all in the center. Because these are moving all over the place, they're feeling a greater pull, and that's making it smaller on there. Does that make sense? It's opposite of what you expect, right? Because if you expect more protons and more electrons, you expect the size to be bigger, but it actually gets smaller. Now the mass is getting bigger though, which means if we were to figure out like how much this mass is, this would be much more than this one because that has 10 protons and 10 neutrons, right? So its mass is around 20. This mass is much lower, right? It's somewhere around 6, 7, depending on how many neutrons it has. So even though this has a larger mass, its volume is smaller. Does that make sense? Okay, so that's what's happening in there. So you have it more spread out, less spread out, and then it's the closest once you get here. Okay, so nuclear charge, we talked about it a little bit. It's the charge of all the protons in the nucleus. It equals the atomic number. As you can see, as we move across, the nuclear charge pulls the electrons in closer to the nucleus, which causes the size to decrease as you move from left to right. So as we're moving across the periodic table, it's going to get smaller, it's going to decrease, okay, as you're going across there. All right. Now let's talk about going down a group, and this one I think will make more sense. So we're going to compare 3 atoms. The 3 atoms we're going to compare is lithium again, potassium, and cesium. Now with this one, you can draw them along because it's going to be super kind of I think it's going to make a lot of sense how it kind of works out. So lithium still has 3. How many electrons in the first energy level? 2. Second energy level? 1, right? Okay. What about potassium? It's got a lot, right? It has 19. So that means its nuclear charge is 19. First energy level has 2. Second energy level has 8. That's 10, right? So if that's 10, we need 19. Another energy level would bring it up to what? 18. And then we need one more, right? So what's the trend as we move down here? It gets a lot bigger, right? It gets a lot bigger, all right? So it gets a lot bigger. And if we had the room for cesium, it would be huge, right? Because cesium has 6 shells, all right? This one only had 4. So as you can imagine, each time you add another energy level, it's going to get pretty big. It's going to get pretty big. Okay, so they're all neutral again, right? So the charge didn't have anything to do with this. But as you move down, the addition of energy levels causes the size of the atom to become substantially larger, all right? This is due to the shielding effect, where lower energy level electrons block the pull of the nucleus from the valence electrons. So in here, the first energy level, if you kind of think about it, these electrons are spinning around here real quick. They're blocking these electrons from feeling the nucleus as much. So each time you have another energy level, the one that came before it is kind of blocking the pull of the nucleus, all right? So if it's blocking it or shielding it, it's not going to be as tightly bound to it. It's going to spread out a little bit more, all right? Because again, it's all about the negative electrons feeling the pull of the positive nucleus, all right? And like for this one, there's not a lot of shielding here, all right? So we only have 3, but then as you get more and more energy levels, you're gonna have more and more shielding, so it's gonna get bigger, all right? And you can also just think of it as more energy levels, it takes more space to draw a new ring, all right? Okay, any questions with any of those two? No? Okay. All right, so this is kind of like a periodic table where instead of showing you what element it is, it shows you about the size of all the atoms. So you can see as you move across, what happens to the size? Yeah, it decreases. And then as you move up, what happens? It also decreases. It's weird that I know we're talking about it going up and across. Well, the across makes sense, but we're talking about it going up instead of down. But if we were having it go down, these two words would be opposites, right? One would be decrease, one would be increase. So if we actually have the arrows go in these directions, they'll always match up, all right? And there's a few of these different trends we're gonna go over. So it's less to memorize if we just kind of have the arrows go up. But if when we talk about it, we makes more sense to talk about it going down though, right? Because here there's only one energy level, then you have 2, 3, 4, 5, 6, and you can see that it gets bigger the more energy levels you have. And then as you go across, it gets smaller because of that nuclear charge pulling all the electrons in closer, all right? Got it? Okay. All right, so for this unit, we're gonna focus on bonds between atoms. We're not going to focus on full molecules. We're going to go over full molecules when we do molecular geometry. All right, so we're going to keep it pretty simple right now. And don't worry, it'll get a little bit more complicated, a little bit more interesting when we get into the molecular geometry unit. So electronegativity is a measure of the tendency of one atom to attract or pull electrons that are bonded between two atoms. All right. We talked about electronegativity last year when we did water. All right, we talked about water and it pulling electrons toward it. The oxygen pulls electrons towards it. The hydrogen kind of lets the electrons go away from it. All right. So imagine two atoms bonded together. If one atom has a higher electronegativity, then that atom pulls the electrons towards it. The other atom would have a lower electronegativity, which results in that atom's electrons spending less time around it. We use the Pauling scale to measure this, and it basically gives every element a number. You'll always be given this chart, all right? You'll always be given this chart, so you can always figure it out. But if you kind of look at this and we talk about the trend, you'll know where the higher numbers are and you'll know where the lower numbers are once you memorize the trend. So first off, fluorine, it's the most electronegative element. It's assigned a value of 4, and the values, they go down until you get down to cesium and francium, which are the least electronegative at 0.7. All right, so it goes from 4 down to 0.7. All right, and if you look at the chart, you can really see what's happening there. All right, you can see the trend. Fluorine is 4, and then down here, francium is 0.7. So as you move across, what's the trend? Yeah, it's increasing. All right, and as you move up, what's happening? It's increasing as well. All right, what do you notice about the noble gases? They really don't have numbers. Some of them, later on when you get into like AP and stuff, some of them do have numbers, but generally, we're gonna say they don't have numbers because the noble gases don't form bonds usually, right? That's what we're kind of learning in honors chem. AP chem gets a little bit more real. Okay, so as you can see here, fluorine, because it's over and up, it has the highest number, and then cesium, francium are the lowest because they're to the left and then down. All right, cool. And we saw this last year a little bit in when we were talking about water. Okay, all right, so we got all that. Electronegativity, it helps determine if a bond will be nonpolar polar or ionic. All right, three terms we talked about a little bit again last year. To determine if a bond is nonpolar, polar, or ionic, you need to determine the electronegativities of each element and then find the difference between them. If there's a difference in electronegativities of 0 to 0.3, then it's going to be nonpolar. And this results in an even sharing of electrons. All right, so they'll share it evenly. And this is because the pull is not strong enough to cause an uneven sharing of electrons. All right, so what is all of this going to look like? I'll show you in a sec. Polar molecules, when the difference is 0.4 to 1.9, these are considered polar bonds. This results in an uneven sharing of electrons, and this is because one atom is more electronegative than the other and can pull electrons towards it. So let's take a look at this polar example. First up, we need some numbers. What's hydrogen's number? Good, yeah, it's 2.1. And then what's fluorine's number? It's 4. Nope, 4. Okay, so which is more electronegative? Fluorine. Okay, cool. And what's the difference between these two? 1.9. All right, so it's 1.9 and it's being pulled in this direction, right? It's going towards the fluorine, okay? Because the fluorine's the more electronegative element here. That means that this is going to have more electrons around it, right? Fluorine's going to have more electrons around it. The hydrogen's going to have less electrons around it. Now, because it's 1.9 and polar is anywhere from 0.4 to 1.9, we need to show that it's actually polar. And this you might remember from last year. We started to use these symbols. We'd show that it was slightly negative if it had the higher number, and then it would slightly be positive if it had the lower number. Because more time out of not, the electrons are hanging by the fluorine. That makes them slightly negative. And then this is slightly positive because the electrons are not hanging out over there. Any questions with that? No, you remember that from last year? Last year we did it with water, so let's take a look at water as well. Again, we're only going to look at 2 bonds. We're not going to look at the full molecule right now. What's oxygen's number? Yeah, 3.5. Hydrogen's 2.1. All right. This one's higher, so it's more electronegative, meaning it pulls electrons towards it. Okay. What's the difference between the two? 1.4, which is in the range, right? So same thing. The electrons are going to be hanging out towards that oxygen more. The oxygen's going to be slightly negative. The hydrogen's going to be slightly positive. All right. And that would be a polar bond. Yeah, Scotty.
What happens if it's over the polar range?
It's a great question. If it's over the polar range, meaning it's 1.9 or above, sometimes they'll say it's 2 or above, it's considered ionic. And we talked about ionic this year a little bit, and ionic basically means one atom rips an electron off and as a result gains that electron, and then the other atom loses an electron. And this is because the electronegativity difference is so strong that one atom has enough energy to pull it off. All right. Okay, so let's look at this right here. Sodium, how many valence electrons does sodium have? If we look at the periodic table, you remember from last year, group 1 had 1 valence, group 2 was 2, then it jumped, and then there was 3, 4, etc. from there. So sodium has 1, all right? Sodium has 1 valence electron. How many does chlorine have? It has 7, yeah, exactly. And let's look at their numbers. What's sodium's number? 0.9 maybe? What about chlorine? 3.0. All right, we subtract those two. What do we get? 2.1, right? The difference between them is 2.1. All right. Which means it's in the ionic range, right? Chlorine's strong enough to rip off that electron. So this electron's going to go over to the chlorine. All right. When that happens, the sodium becomes what charge? It lost an electron, +1. And then the chlorine gained an electron, so its charge is going to be -1. And then they're going to stick together because of opposite charges, right? And we did this a little bit when we talked about nomenclature. and a little bit last year when we did something very similar. All right. The difference this year is now we're talking about electronegativity numbers. All right. So you have to check the numbers first to make sure that it works. Because last year we just said if it was a metal and a non-metal, then it would form an ionic bond, right? This year we have to actually check the electronegativity chart to see if it's above 1.9, and then it would be ionic. All right, which means sometimes a metal and a non-metal can actually bond covalently depending on their electronegativity charges. All right. Okay. Any other questions with that? No. All right. So here's their electronegativities in a fun little graphic here. As you go across, what's happening? It's increasing. Yeah. And then as you go up, what's happening? Increase. All right, so it's increasing both ways. Okay. Any questions with that? No? Okay. So, electronegativity and electron affinity connection. Ionic compounds, these don't share electrons and they're formed from the loss and gain of electrons. One atom has a much higher electronegativity and pulls an electron completely off a nearby atom. All right, so that's the definition of an ionic compound. All right, ionization energy. This is the amount of energy needed to remove an electron. This amount of energy is needed to form an ionic compound. The higher the electronegativity, the more tightly the electrons are attracted to the nucleus, so more energy would be required to remove the electrons, thus a higher ionization energy. The lower the electronegativity, the less tightly the electrons are held to the nucleus. So they would need less energy to remove the electrons, and that means they would also have a lower ionization energy, all right? So in this case, the metal side of the periodic table generally become positive because they have lower electronegativities, and then the non-metal side generally become the negative ones because they have higher ionization energies and higher electronegativities. So it all kind of works together in here. The last thing we're going to talk about right here is electron affinity, and that's how likely it is for an atom to gain an electron. It's more likely for metals with low electronegativities to give up electrons. They have a low electronegativity, so their electrons are held less tightly. It's less likely for nonmetals with higher electronegativities to give up electrons. These atoms have higher electronegativities, so their electrons are held more tightly to the nucleus. So you may be like, well, you just said that. And yeah, the whole chapter really relies on atomic size and electronegativities. And so if you have a high electronegativity, everything's being held stronger. It's less likely for you to give up an electron. It's more likely you'll gain an electron. All right, so ionization energy trend. As you move across, what's happening? Yeah, it's increasing. And then as you go up, it's increasing as well. All right. So as you can see with this electronegativity, they're very similar because they both increase as you go across and as you go up. So far, the only one that's been opposite is atomic size. Okay, and then there was electron affinity, and this one, as you moved across, it also increased, and then as you moved up, it increased as well. All right, so we have that going there. All right, and then bringing it all together. So we have nuclear charge and electronegativity. Since the atoms on the right side of the periodic table have a smaller atomic size, their electrons are closer to the nucleus, which causes these atoms to be less likely to lose electrons. As a result, the nucleus holds onto their electrons with a stronger pull. This is why they have higher electronegativities, higher electron affinities, and higher ionization energies. All right, so it's all about them pulling together. And throughout you reading the chapter and going through the winter break work, this should make more sense when you actually understand or have at least memorized what these terms mean. All right, that'll make it a lot easier. All right, but I wanted to give this overview today just to kind of like help you see like what's the big picture with it all. All right. Okay, so electronegativity. The atom with the higher electronegativity has more electrons near it because its highest energy level is closer to the positive nucleus. The electrons spend more time on that atom, so they can be closer to the nucleus. Higher electron affinities, since the atom is smaller, it's more likely it will gain more electrons, since the new electrons would be closer to its nucleus. All right, and this is kind of why it